Good morning, everyone. Welcome back to the session 2, 3D modeling design using PTC Creo, online faculty development program on augmented reality and virtual reality, sponsored by AICT Atal. I welcome you, sir, Chaitanya. You can continue the sessions.
Okay, let me start by sharing my screen. Yes, do let me know if you are able to see my screen. So is my screen visible? Hello? Okay, so I just received a confirmation from Mr. Ajay. The screen is on. So yes, so in the next part, so I just wanted to demonstrate how you can develop some 3D models, basic modeling features. And so it would take a bit of a practice and also what we actually want as a design. So there is nothing like a limitation in a 3D modeling software. So pretty much whatever you are able to sculpt or put it on a paper can be definitely been brought into the digital 3D model space as well. So here we are going to take an example of a C clamp. Okay, so what you are seeing on the bottom right is the actual product. Okay, so this I have picked up it from the PTC tutorial itself, what was available with me. So we have already, so the product is already existing. Let's say we want to rebuild the models into 3D space and assemble these things. So this is a quick demonstration that I wanted to take up. So next, so we have part drawings. So let us start with a spindle. Okay, so maybe I can grab a screenshot of it. So this spindle, so as you can see, it is a shaft. Okay, so it has three diametrical steps. So diameter 6, diameter 12, on which there is a thread over the entire length until this point. So it is an M12 thread. Okay, I will show you also a demonstration of generally, since metric threads or any kind of threads are standard, so we just represent it in terms of a cosmetic way. Though visual representation of the grooves is not ideally needed because it is already fed. It is a very common practice for the manufacturers to develop threads, and it is also fed into the CNC. So they can just select the shaft and they can give the pitch and the machines or the pitch, then they can refer to the standard. Okay, and that actually does more of a good job so that we do not mistakenly give the wrong pitches or grooves, and because the mating nuts and other things, they're already industry standards. Okay, and we have finally head wherein we are able to insert the handle, so for the operator to unlock or tighten the job. Okay, so let us take this example. So in the previous demo, we had seen an extensive use of the extrude command. If you see, this is a circular component. So I wanted to demonstrate another very commonly used feature, which is a revolve command. Okay. So again, I bring my Creo window. So let us start by setting a working directory. So I will create a new folder. C clamp. Okay, so this is where our fold components will get stored in. So I'm going to say new. Okay, so this is spindle. Okay, spindle C clamp as a lambda. Okay, I'm going to select metric system as a template, so that we'll have all the dimensions in millimeters. Okay, so we can also start by assigning the raw material. And yes, to answer one of the question what I had in the past session regarding the porous materials, especially bone case. And sorry, I'm just going a step back. So let's say even on any normal engineering material, so let's say foam, it is also a porous material. But visually, what is important for is the outer dimensions. Okay, if it is what kind of a profile it is carrying. So those profiles we should be accurately be representing in the 3D model. So the porosity or the weight of the component is generally taken care by the density. So to answer the question of the bone porous, because we consider all the materials are to be homogeneous, so we are going to take it by the property by the density. But when we are taking this for simulations in the simulation software, so therein we are also able to get some options wherein we can define the porosity or the adhesiveness or the friction of these components. Okay, okay. Going coming to our this thing now. So if you see, so we have a center line on this component of spindle. Okay, and we have this step. Okay, which is pretty much we can imagine. So what extrude does is you have a section in it section in a particular normal to the plane of the sketch plane. So it expands and it extrudes and adds material in that direction. In case of a revolve, what happens is, so you need an axis and a profile, and around the axis the material is generated in the order of that section. So let's say if you have an eye section, so you want to bend or rotate, you have a circular component with eye profile or a pulley. So you give the section of the C or the eye and you revolve it around and you get a pulley. So this I will just look at on shortly. So I will go to revolve. Okay, let us switch on the planes what we have. Maybe we will keep the same orientation. So this we are having in the front view. So I will take this front view. Okay, and this is the way I got it. So we need a center axis for a revolve. Okay, for against which the section has to be revolved. Okay, and let us start from here. So I know that there are 3 steps in this. Okay, so we will dimension this according to the drawing what we have. So this is representing the radius of the component. We ideally want the diameter 20 to be represented on the drawing. So let's take the diameter. Similarly, this one and this one. So we have the diameters. Next, we will take up these dimensions, steps of 3. So this is the dimension. So this you can, so it all goes by the click of, by the way we are sequencing the dimensions. So here I have selected the curve. So it is giving me the length of the line, the curve. In the other case, I have selected the center line in combination with the vertices. So it is giving me overall diameter instead of a linear half dimension. Okay. There we go. So now, so what would happen is, if you see they are very big dimensions. So if I try to So this is 20, right? And it is shown as some 240 odd dimension. What will happen when I give this? It will go something in this order. So it will regenerate as soon as we are in giving the input of the dimension. So there is a small technique what we follow. So I am selecting the dimension filter over here so that I can select all the dimensions. Okay. This is also something similar to AutoCAD where we work generally on the layers. Okay. So now I go to modify dimension. Where is just a second. Yeah, sorry, here it is, modify. It is hidden with this ribbon. Okay, let me take up this. Okay, so here I will turn off the regenerate option. Okay, so I will update all the dimensions. So we know that this is 20, and next is this step, which is M12, and next we know that this is 5. Maybe you're following it. Sorry, this is 6. So we have done 20, 12, and 6. Let's update this as 6. You see, the dimensions are being updated, but the geometry is not getting regenerated. Okay. So next, 103 is 22. We have 96 and 12. Okay. So this dimension is 22. This dimension horizontal is 96. And lastly, this is 12. Okay. So now once I say okay, you see they have all regenerated itself. Okay, now we have a component that is representing the revolved section of the feature, revolved section. Okay, fair enough until now. So please drop in questions. I have the question and answer window also on the side. So now you see this has revolved against this axis. So it has made a complete 360 degree. Let me see if I make it 270. You see, we can stop it at this position, but we know it is a spindle shaft. It's a circular rod. We're going to use 360. Okay. So it has revolved the section around along the center axis what we have given. Okay. So next we'll go to the other features. Okay. So we know that there are through threaded two threads. One is an M12 and one threaded portion, which is M12, and it is starting at this portion and stopping just ahead of 3 millimeter from this shaft. Okay, so there, like I said, there are two ways. Either we want to represent it is visually, or we can also just put a cosmetic thread in which it on the drawing it will be automatically shown that there is a thread there. So I will show you both ways. So first let us take up this hole because it is a very through hole and a very simple one, dia 5.5. So I will again switch on the planes. Okay, so if you see the orientation, so if you want to now just look what the front view is. So right now this is the front view, this is the back. I want to see the right view. Okay, so and I will also show on the assembly or on the part level itself how we can make a sections and see how the interactions are going on. So next, so we took a revolve. We can either take a whole command or an extrude. So maybe I can just take a extrude. I will take this plane, this center right plane, front plane. Okay. Let us switch off the coordinate system. And this little guy is 5.5 mm hole. Let's give it as 5.5. And we have a dimension feature referring from the base of 11 millimeter. Okay, so this I've picked up a dimension. I will take this surface to this point and measure it as give the linear dimension, and it is as 11 mm. Okay, so now I click OK, and as you can see, the remove material, it has sensed that we are creating this feature inside a solid block, inside an available material. So it is asking us how much in what directions. So if you can see, I can either do it in this way through, but ideally I would prefer, since this is a parametric model, and let's say in the future you want a diameter which is 100 mm, right now it is 20 mm, the head. So in that case, maybe the whole may be suppressed within inside. So I will use a command so that even in a future modification, we are able to always retain these holes. Okay, we don't want to edit it, and the model is regenerated along with the hole is regenerated as and then the diameter is also changing. I've given it as a through hole. Okay, yes, and along with this, we also have a small chamfer feature. This is a 2x45-degree chamfer. So generally, chamfer's radius we put at the end of the model because they are they consume a lot of memory, and so we want to first fix the sections and then do these things. In this case, the thread is still not applied, but just I wanted to demonstrate some things on the thread. So this is 2x45. So we can, so there's a d by d. So let's say if I select d by d, it will take equal mm, 1.6, 1.6. d1 by d2, you can define one length and another length, maybe a 3 mm, something like this. Okay. So on the drawing, we have angle by d. So angle is 45. Okay. And the length is 2 millimeter. So it is a case of d by d only. Okay. And we have a chamfer here. Okay. So now coming to the threaded portion of it. Huh? Let me show. So one is what we can represent visually. Okay. So we are going to cut a groove across the thread. For normal screws and threads features, it is no more a general practice to show this on the CAD models, but we'll just for the sake of seeing the available commands, I will just take you through. So if you see I've took you into the volume helical sweep. I don't know if this is visible. Yeah, volume helical sweep. Okay, command. So it is asking you want a left-handed or right-handed. So all screws are generally right-handed screws. Only very specific applications wherein you don't want the operators to, or by mistakenly loosen the components, we go for a left-handed threads. But all the standard threads are generally right-handed. So it doesn't hex profile. So what is it is generally saying is along which line or the pitch you want the helix profile unit. So I'm taking this. Maybe it would be more clear once we have. So we want it on the surface along this axis. Okay. So I'm selecting the right plane or the front plane. Sorry. Okay. And let me also take this. And we know that the thread is starting 3 millimeter off this head. Okay. So it would be also wise to just consider a line. Sorry. A line that is starting from here, and let's say in this case we just extend it a little ahead. So this portion we know is 3 millimeter. Okay, and let's say I define this a little. I also extend this a little. Okay, maybe 5 mm. So here we have the helix. So this is an M12 thread. So M12 generally has a pitch of 1.75. I can have this pitch over here. helix axis. Let me select the axis. I give the pitch. So it is taking a pitch of by default of 32.75. Let's see this. Mhm. Just give me a moment. So we also generally have to consider that. Okay, for some reason it is not allowing me to change the pitch value. Let us try once more. I go to sweep, volume helical sweep. I take references. I define the position, right. We're going to extend it. Okay. This is at a distance of 3 millimeter. You want the thread to cross the shaft so that there is a start. The tool is able to pick it. This is 6. I also give a center line. Okay. This is here. 1.75. Yeah. So now it has, I don't know if it was some kind of bug. So if you see, so maybe now you can appreciate what it is trying to do right now. Okay. So along this axis, we wanted a helical groove. So the helical groove is going to follow a particular profile. So this profile is extending from this along this line, and it has a pitch of value 1.75. So this is the standard pitch for an anti screw. Okay. And now we want to cut a groove inside this. Okay. So I will, so what kind of groove? So we know that we have different kinds of threads, UNC, buttress thread, or metric thread. So in this case, we are going to follow a ISO metric thread. So I just also tried to capture the profile. So you see the included angle as 60, and the depth of cut is approximately 0.5 times of the pitch. Okay. So maybe we can just consider this for time being. I will define a sketch. So it has taken me into the sketch mode to give the section. So I will cut a thread in a triangular format. Okay. So we are taking an okay, and this we are taking 0.75 by 2. Before that, so now I'm also, so this is going to be an equilateral triangle. So I'm going to give an equal length. Okay. So that is good now. And please bear in mind, I'm just giving the basic features of the metric thread. So the included angle. So the depth is generally around 0.6 times of the pitch value. So in this case, I'm just going to consider half of it. Okay. So now we have, so if you see, we have a helical. So this section is going to revolve around that profile, the helical groove, and make a cut there. Okay. Now I say okay. And again, something is not right. Just give me a moment. Okay, let me see the 3D object of it. Okay. So it has taken the center line as a along itself. Huh? That is creating the problem. So this center line, we had to select the other one. Okay, this is good. Mhm. Okay, my bad. There is something going wrong here. Uh, okay, maybe I will just back to this feature of this not to put more time. So let us just quickly go through the cosmetic thread, what is general practice. Okay. So engineering, we get a cosmetic thread here. Okay. So this generally asks to define the thread. Okay. When I select the thread, it is by default taking. So again, it is asking from where you want to start the thread. Okay. So I'm going to start the thread from here. So this says, and it is asking now again to select the threaded surface. Okay. So I select here, and this is my threaded surface. And now it is taking until which value. So it has considered the entire length, but we know from the drawing that it is stopping at a distance of 3 mm. So not the entire length of 96. So we will stop it at 93. To select from the list of already available threads. So here the list of cosmetic threads are the available standard threads are already there. So we know that M12 we are considering 1.75 pitch. So there we go. So if you see this, it has considered a cosmetic thread by itself to have to construct a metric thread of M12. So when I say OK, so the cosmetic thread is already formed. So, but if you see visually, it is not visible. Okay. And but if I, let's say, if I try to, yeah, hide this, the geometry. So you can see there is a thread that is already being formed. So this is already identified by the suppliers by the CNC. So it is not a big deal to have a visual representation. Okay. So we have the spindle ready. I will save this model. So it is getting saved into the directory what we had already made. Okay. So any other features we are missing on this? No. So this I think is good. So we'll again take a new component. So let's say we are going to take up maybe the handle portion. Okay. So I will take the handle. It's a simple shaft. So either we can do a extrude or a simple revolve. Okay. So I know that this is a diameter 5 with a length of 96. Maybe an extrude would be a good way to do. So I'll take handle. I'll give the description as say clamp template. Let me change it to this thing. So yes. So let me switch on the planes. So I will take the front plane, or I can also take the right plane. Yeah. I'll take an extrude. Let us make a, so this is quite an easy model. We have a 96 diameter. Okay. Plane along the right plane. Sorry, in diameter is 5. So the length is 96. So it is now asking me to the direction of rotation, extrusion. Let me consider both directions and I will give it as a 96. Okay. So here we have this component. And we know that on this both ends we have threads. So on these threads, the end handle caps are getting mounted. So they are getting screwed to this M5 threads. So this is an M5 thread of a distance of 5 millimeter. So let us use cosmetic again, cosmetic thread. So like I said, we'll select ISO. So it is asking where the thread is going to start and on which surface we want this. Okay, it has considered the entire length, but we want it only until 5 millimeter. And this is an M5 thread. So M5 threads usually have a pitch of 0.5 as a standard coarse pitch. Okay, you see this has been generated. Okay, and again, so here now you have two options. Maybe you want to remake the same feature, or you can also mirror it. So if I take mirror and I will switch on the planes, so it is going to ask me the mirror plane. So we have the thread over in this direction. I can select this and you see. So if there is a lot of work and it is a symmetric part, you can use the mirror command just to replicate the features from the one side to the other side. And there we go. So we have a shaft that has M5 thread and over a length of 96 with diameter 5. Okay, I will also save this component. Next, we'll move to the spindle cap maybe. Okay, so this spindle cap has a taper. Okay, So it has a diameter 11 at the bottom and diameter 20 at the edge, and it has a counter bore inside. Okay, so the counter bore inner diameter is 6.5 and the outer diameter is 14. So this spindle cap is getting attached to the spindle. Okay, so it is attaching to this portion. So we'll just have it there. Okay, so file new part, spindle cap. See, okay, I'm going to select solid part. Yes. So we can probably use the revolve command straight away. Okay, so since we have an access and we can build this section inside the revolve command. Well, let me take the front view and use revolve. Okay, I keep it in this format. I will turn off the planes. So we need a center line as a prerequisite for a revolve command. And let's take a look at the section ones. Yeah, what we see that it has a profile, it has a counter bore, it's going away. So in this case, the counter bore and the outside are at the same depth, outer diameter. Okay, so the center line is defined. Now we want to define the okay. So let's start at the bottom. We have bottom diameter 10 and full depth and 2.5. So just let us first put the dimensions in place. So see, now it has taken from center, but we ideally want a diameter to be placed. So if you can see what I'm going to do, select this, and again come back to the center line. So it gives me the diameter. Okay, so I get this, select this guy over here. I select the diameter over here. So what we are left with are the internal diameters. Okay, so this. Okay, so again, I will just try to put the correct values. So this is 11. The height is 10. This, okay, so if you see, it is getting automatically regenerated. So it is causing confusion. So I will just undo it. We have to just uncheck the regenerate. Okay, I will again start. So it's 11. You see, this is 10. This is 2.5. Now we are looking at this diameter, which is 20. Inside diameter is 14. The innermost diameter now is 6.5. So maybe now I can regenerate it. You see, it's regenerated into this format now. Okay, just to appreciate what it is trying to do. So it is trying to revolve around this axis. Okay, so I think that is good now. So I will just give it a full 360-degree turn, and here we have our component. Right. So any questions that are coming up? And now we are left with two more components. Okay, so we'll take the handle cap here. So what we see, it's a circular cap which a depth of 5 millimeter inside. So maybe this we can create with a standard hole, and this we can use an extrude feature to develop this. And it also has a chamfer in the ends. So I save this model. Okay, it has been saved. I go to new part, handle cap, length. Okay, does not allow me to give spaces. I can take MMNS part solid. Okay, and yes, we'll use an extrude. So we have a circle of diameter 10 extruded to a length of 10 millimeter. Okay, so let me switch on the planes. We will take the same orientation. So in the front plane, sorry. So we want to change the orientation, change the sketching plane. Okay. Um, since we are using extrude command, so I will switch to right plane. Okay. So this is diameter 10. Extended to a diameter 10. Okay. And in this, we have a hole in the end. So we can also use a hole feature. If you see, this is the hole command, and it is located on this portion. Okay. So it is asking us to take the references. Maybe I can take a reference of this in the right plane. And since we know it is exactly in the center, so both we can give as center. And now we want to as a, if you see there's some predefined profiles, what you can choose. So we will take a standard hole, and it is a threaded type. Okay. So now it is asking us what kind of thread it is. So it is a hole in a thread of M5. So M5 by 0.5. Okay. And it is also asking us the depth of the thread. Okay. So if you take this, the depth of the thread is the bore inside is 5 millimeter. So I'm going to take a 5 millimeter. Okay. So if you see this, it has given us, this is an M5 ISO tap, and the depth of is 5 millimeter. It's also suggesting the kind of drill that we can use with this hole. It's suggesting to use a 4.5 mm drill. So that on the 4.5 drill, again, they have to do the tapping to cut the thread in the helical grooves. Okay. So, and last thing that is left out is this chamfer feature. So chamfers are generally used to avoid sharp edges for someone who is touching. So that is the reason we cut off the sharp edges. Okay. So let us take the chamfer command. It is 45. So angle by D, I give it as 1. You see this. And one other, so if you want to see how I mean, we can actually go inside and see what is going on inside. So we can also do cross sections. So the cross section is a very basic fundamental of engineering drawing. So we want to give a detail of the inner portion. So I can take a cross section, let's say section A. I select the right plane, and you see, I can see the cross section, how it is there inside. So this feature is coming as a manufacturing output, since the drills have a conical ends. So it is already known that we cannot have blind holes are costly compared to a normal. So we may have to pick up a specialized tools, milling cutters. So this is a normal drill with a conical end. So that is why, if you see now, if I want to measure, okay, so I measure the diameter is 10. I can measure. So this is including the chamfer. So the total length, if I want to measure, it is 10 millimeter. the inside length is 5, and after that there is this extended portion of the tool. So let's say this is a tool a feature that is already being formed on it. Okay. So I will turn off the section. So I save this component. I think now we have 4 components that we have made ready. Okay. So now we have the C jaw that we need to do. Let's go back to drawing board. Yeah. Now we have the clamp jaw. Okay. So this, if you see this particular part, so we have a C profile. Okay. And along with that, there is also a T section that is going on. Okay. So what you see, this portion, it is adding to the moment of inertia of the component. So it is not allowing it to bend when it is getting tightened further. And also it has a screwed hole for the handle, for the clamp handle to be inserted. So the clamp handle will go like this inside this. Okay. And on this we have that spindle cap. Okay. So in between this, we have the job that we want to arrest or lock to do the job, to do some operations. So yeah, so let's get started with this. Okay. Maybe we can pick up with this section, okay, which is where the spindle handle is going to meet. So this particular feature, so it is at a distance of 75 from bottom, okay, and it has a length of 23, and the upper radius is R10. Let's go again. I will save this part. Component. I'm picking MMNS part solid. Okay, so what we know is this feature. So let's say if this is the center plane of the component, which is our, let's say in this case, the right plane, and we want to do this feature. Okay, so we may want a plane at this portion. Okay, so that we can create this feature at an offset from this center plane. Okay, so this is a symmetric component. So we can, this is 37.5. So we want to create an offset plane which is parallel to the right plane. Okay, so let me switch on the planes. Okay. So this is the plane and we want an offset plane. So I select this. So now I want a plane in this direction. Let's say 37.5. Okay. And on this plane, I would like to create the feature, this feature. Okay. I take extrude. Let us put it in the direction. Okay. So first let me take a center plane because we are going to make a symmetric part. Okay, and I make an arc and I delete this thing. So we know that this is at a distance of 75, this distance. Okay. 75. And we also know the overall length of the part, which is, okay, so we have 75 and 23. So this is again adding to 23, 75, that's 23. So we will also like to add this here, which is 23. and the radius is 10. Okay, and we see there is a small mismatch between the lines, so this we will try to trim together. Okay, so there we go. So a small portion. So now we are good with this. Okay, so we have a 75 at a distance of 75. We have the section for the hole, and which is with the radius R10, and this is a depth of 25 millimeter. Okay, so I do this. So we are going. So our right plane is over here. So we want to do this on the opposite side and give it as 25. Okay. So next we will do this T profile. So this uses a sweep command. So this T profile is going in this format up to the top. Okay. So first we may need to define the trajectory, just like in the helical sweep. So in which, what should be the trajectory along which the section should follow. So let us define this. So it has to be going in this format. So it has a R30 and it is goes up and it is goes as still as 100 millimeter, the T section. So let us try to make the trajectory first. Okay. So I will take the front plane. Okay. So this is the, when kept in the default orientation, when I see this is the front plane, I select, I draw a sketch. Okay. I take references. I want to start from here. Okay. I draw a center line also. So from this point, I go up. I know that this is symmetrical. So I select symmetry and give symmetric. And this overall length is 100 millimeter. Okay. So 100. And we have radius here, which is R30. This and this, the outer radius is R30. Okay. So we can select a fillet command. So this and this. Okay. We lost the dimension, which is 100. And now since these both are equal radius, so equal dimensions, I can use the constraint of equal. And first I would like to make both as equal. Okay, so now you see only one radius that is being visible, which is 30. Okay, and this overall length of the comp is what it is asking for. So it is considering 70. So it is 75 plus 25. Okay, so 75 plus 25 plus 25. I can mark it as a strong dimension in that case. And in either case, since this is already defined, we can also avoid this dimension and give a symmetric. Okay, so I take this and I say this point and this point are symmetric to each other. You see there is a small constraint symbol that is getting highlighted here, which is symmetric symbol. And this implies a tangency, that this curve is tangent to this vertical line. So this forms our trajectory. So the T profile, what I was saying, this profile is following this trajectory. So we have the trajectory. Now we need just the section along with which this should be going. I get into sweep command now. Okay, so it has selected the trajectory because it was highlighted. Okay, so now we have to just create the sketch of the section. So I take sketch. So it has already it got itself into the sketch mode. It is asking us to draw the sketch. So if you see, this is a T. So here I also wanted to show some already available standard sketch profiles. We can pick them from the palette. If you see the palette, you have a triangle, polygon, and some profiles. So the profile, I can pick this up. Okay, I place it here, or we can also draw it by hand. So it is up to the convenience of the user. And I place it here and I say okay. So quickly I will again use the commands to constraints. So this line has to line over this vertical line. I use the coincident. So I use this and make it coincident. I use this line and make it coincident. So it is giving me an error. Okay. Maybe we can delete that dimension for now. And this should lie over this. Okay. If you see this tree section, it is completely on the edges. So the only dimension I think what we have is the 6 millimeter. So we just need to define the 6 millimeter. I give this, which is giving me an error of 8.77. What is happening here is it is taking an equal constraint. So it is saying these both are equal, and that is why it is restricting us. So we can just delete this equal constraint. Okay. So I give this, which is 6 millimeter, and this height is is this one, this depth. Okay. So this 5 millimeter is getting transferred from this view and going into the same, okay, which is 5. So there we go. So we have a C profile, which is a T section, which is following the trajectory what we have given. Okay. So let us measure the dimensions over now. So I will just quickly take this. So this should be 6, okay, and this should be 5 millimeter. And also we will measure this, which is 5. We also have the radii defined over here, if you can see, which is R5 and also R10. We can also just verify if it is following this. So I will take this one. So this is diameter 10, which means the radius is 5. And similarly, this is diameter 10, the radius is 10. 20, so the radius is 10. Okay, so we have now a fair look of how the component is going to look. Okay, so now we'll proceed to the next features. Let's say now we want to do this hole. Okay, so this hole is a M12 hole again. So M12, we have taken a pitch of 1.5, 1.75. Okay, so let us establish this hole. I can hide this sketch for now. Okay, I'll take the hole command. Let me take this. It's a standard thread. I'm interested in M12 by 1.75. Okay, and it is asking me for the reference. So this is 0. Okay, and the other reference, I'll take it. I can take as the surface. Maybe I can create an axis. Okay. And I give this axis, which is again, sorry. Okay, which is 0, and this is also 0. No. First, let's select the right hole. Okay. This is 0. Move. Okay. Yes. So maybe this is we can consider the center point, so which is at a distance of 13, or I can do it in another format. So maybe I will create a point over here. Since we are not able to pick, I will select this axis and this surface. So we have a point at the center. Okay. And this point we can use as a reference to place the hole. Okay. So placement, I can say on point. I will highlight the points. Yeah, it has already picked up the point. And I say this as M12. And this is a through hole. Okay, so when it is saying through hole, it is also taking the other one. I'm going to just say up to next. Okay, so still it is taking a through hole. Maybe I can take up to selected, and I give this. Point. Point has been selected. So we have the hole on the point. So basically, it is giving us a, so what we want to change here is we want to make sure that it is not blindly going away. We can select the surface up to which we want the threaded hole, and this we can give. So it is a through hole with an M12 1.75 thread. The next feature would be, I think we are left with only this chamfer feature, which is of 20 by 20. Let me turn off values, chamfer. In this case, you can take this. Okay. And yes, we have this ready. So we have all the components now. So we will quickly get into the assembly mode. So going back to the presentation. So we want the components to be assembled in this format. Okay, we'll start with the C, then put the spindle, and then the spindle cap, and then the handle and the handle caps. Any questions until now? So we are done with the part modeling.
No, Chaitanya. There is no questions in the chat window.
Okay. So we'll call up the first component. So this is the assembly. So this also remains the same pretty much in any kind of 3D modeling software. So I will try to call in the components that we have just created. So it is asking us from our directory what we want. So I'm starting with the clamp. Okay, so in general, the very first component, we keep the default position. So what happens is the coordinate system of this component and this component are going to meet with each other. So you see here by default it has already taken it. Even if I do not do this, let's say it is somewhere here, I use the default command for the very first component, it is going to come and sit in the same position. Okay, so there it is. And it says fully constrained. So if it is say, let's say going forward, I will show you with other components. So unless and until it is fully constrained, just imagine that there's some degree of freedom is left aside. Okay, so next we'll bring the spindle. This is spindle. So we know that. So in terms of a layman, I want it somewhere over here, right? It has to be over here. Okay, so in this format. Okay, so to do that, we have many commands. So first thing is we want this hole and this hole to be coincident. So I'll select component surface, which is this surface, and I'll select. And if you see, this is set into automatic mode. So the software also tries to analyze what we are trying to see, and it will fit in the best possible constraint that is possible. So either I can first go, I know that I do have to do a coincident, I can select and then proceed. Or if I know that the software is able to identify this, I can just leave it in automatic. Just watch this. So when I select this, it takes as coincident. Okay. So now if you want to change, still there are some other options that no, I don't want this to be coincident. It has to be tangential. So those you can change. Okay. So next, so now you see this is gone coincident with this. So now let's say we want a reasonable amount of space that should be left between both of them. So this surface and this surface, again, it has taken coincident, but let's say we want a specified distance to put a job by default. Let's say in this case, I give 50, or let's say 35. Okay. So if you see here, okay, so it is saying it is fully constrained. So we had just given the distance and this, but it has made some assumptions. Okay. Remove this, you can see that still it has the freedom to rotate in this direction. Okay, so since I know that this degree of freedom, so now it is saying partially constrained. So maybe we want it always in the horizontal mode. Okay, if you want, we can also give that constraint. I will switch on the planes. Okay, I will say this plane, I will take a new constraint. This plane to be parallel with this surface. Okay, so it has taken by coincident, and it is saying you cannot have a coincident axially with a hole and also coincident with this. That's why it says it's an invalid. So maybe I will just say parallel. Okay, so it is always set in the horizontal position, and also it is parallel. The holes are always it is also coincident. Okay, so we can also change the colors of the component. Let's say, so this is the view command. I want to picture this C clamp. I select this. I don't know what happened there. Yeah, so now the color. You may think that there is a interference between this component and this component. It is because it is a cosmetic thread and the material is removed in the actual process. That's why you may think that it is interfering. So this we can simply check by doing a cross section. Okay, I give a front cross section, and you see the M12.75. So this portion will be the screw portion, which will be along the helical groove. Okay. So switching. So we will also bring the spindle cap now. I think is a good time. Spindle cap. Again, the spindle cap has to be positioned. Let's go back to our presentation. Yeah, it is meeting with the end of this thing. So what we can do is first, maybe in this case, this surface is, so keep a watch over here. So it is now taken as a normal. So by time it is assuming that we want it as a normal, but ideally we want it as a coincident. So sometimes it may also happen that it is getting coincident, but it is not happening in the right way. So we may want to flip it out. And the other constraint is this is coincident with this. Okay. So we may want to also give a color to this component over here. Yes, so this is okay. Next, so we want the spindle and the spindle caps are done. We want this handle of the spindle now. I bring this. So there is also a preview view, so that let's say you are not, you want to keep the assembly as it is and you want to avoid going into intricate shapes. So if you switch on this window, it will give you the component in a separate way. Okay. So what it does is you can select from your assembly window the assembly constraint. Okay. I want this hole to be coincident with this. So if you see, it has already come up. And now we are left with a degree of freedom in this direction, which is open. So maybe I can say that this plane, sorry, let me remove this. So we want this plane to be coincident with assembly right plane. When it has gone wrong, normal, but we want to be coincident. Okay. So this plane and this plane, they're coincident, and you see it is fully constrained again. Component is fully constrained with the assembly. So let's say we also want to make another color representation of this. Yes. And now we have finally the caps of the handle, which are these end caps over here. Oh, I think I bought the wrong component. Spindle cap. No. Handle cap here. So again, this is coincident with the inner side of this. So as you can see, it has been bought here. But if you see, this is on the wrong side. So maybe you can just do a flip. Okay. And we know that here we have a counter bore. So maybe we can define it by distance. So this along with this, if you take, okay, maybe I can say it as a somewhere close to 5 millimeter. Okay. So if we have a doubt that if it has been assembled in the right way or not, okay, or if it is crashing inside, we can make a section again in this portion. Let's say this section is B, and it is going to ask us against what plane. So let us select this plane. Okay. And now if you see inside, yeah, it has just reached the end of the thread. Okay. So based on this, you can also adjust the distance, the 5 millimeter what I have given. So another things what you can do with section C is, let's say I'm want to again edit this section. So all the sections are listed on the bottom of the model tree. Okay. I can also see it in a separate window. So while you are rotating it, so the section window profile is shown in the normal. Okay. You can observe what kind of clearances are there, if the thread is fitting, or if you want to do some modifications locally or save some material. So those actions again you want to cross verify. Okay. And similarly, let's, so if there are multiple components that are getting the same components, so now we know that this particular cap is used twice. So rather than doing the whole exercise again, we can also do a repeat. Okay, so we select the component from the model tree or from the directly from the portion here. We do a repeat. Okay, it asks us what commands you want to repeat. So I have a coincident. So we did a surface coincident, and another is the distance. What we did. So we'll do the same, select the same at this end also. I say add. So first is the coincident. I give a coincident, and next is the distance. And you see the component has automatically was put in place. So you can do this multiple times. If there are, let's say, 4 or 5 Cs, you can just start repeat doing this, and then in the end click OK. Okay, so yes, let's give it a color, maybe yellow. This. Yes, so I think that is a fair run of basic modeling features what you could have looked at. So we have gone through simple features like extrude, revolve, hole, if you want to make a thread, a spindle cap, in that order. Okay, so any questions now? So we are almost closing the end of the session now. So this is, yeah, maybe another one other thing what I can show is, so if you want, you can also show an exploded view in this format. Okay, the way it is being shown here. So what I can do, I can go into this, I go to explode, I create a new explode, maybe I'll give it the name, and I will say edit positions. Okay, so what I can move this component aside. Maybe we can follow the same style what is given here. Okay, so I will move the rod away. So this is in line with this and going away. Okay, and this particular portion also I can bring it, move it away, and keep it in this format. Okay, so yeah, so if you see, I say save. Okay, so this is an exploded view. And let's say if I do not want the exploded view, the components will retrieve back to its position. And if you want to activate this, the components have moved away. And to just to show the bomb quantity or an explosion, how many components are involved in this. Okay. And let's say, since now we are in assembly, you want to find the overall weight of this assembly or the CG of this assembly. Okay, so for that, we may want to assign the material properties for each of the component first. So in this case, let's go one by one. I will open file prepare model properties. I say, let's say this is cast iron Fe. Okay. Fe, I say, okay, close. We just verify it again. So if you see, the material is already assigned here. Okay. going back to the assembly, maybe to the handle cap, prepare model properties. Maybe we can give it as a brass, since this is a touch point, maybe to improve the perceived quality. Okay, so this is brass. Next, we take the spindle cap. Maybe we can take it as a stainless steel, not to get rusted. Okay, it is assigned. Save this. Handle could be a normal material. Just want handle is, let's say, again iron. Lastly, the spindle. Okay, so properties, change, and in this case, let's take some other property, Fe30. Okay, so now so let's say you want to know the weight of this component. I go to mass properties and I give the default coordinate system, and you see, okay, here we're getting in terms of tons. Okay, but the center of mass, the density, those are all listed over here. Okay, so similarly, if I now go into the assembly, okay, I remove this explode and analysis and mass properties. So all the solid geometries will be considered. I give this, and you see it is approximately 6.4 kilos, this component. Okay, so it is summing up all the components that have the materials are being assigned, and it also gives us the center of gravity of, of the assembly in this state. So these are commands that are almost, and that would be similar across any kind of 3D modeling software. So not necessarily it one is, so maybe it is more like the usability or the parametricity and the specific applications. View is very good in parametric modeling. So whenever you want modifications or that has to be made, so if you change one dimensions, the other will also easily regenerate. Okay. So questions at this point?
Dear participants, if you have any message in any queries, please put it in Q&A session.
So meanwhile, I wait for the questions. I think I also owe you the history. I got messed up. Maybe I'll try once again the helical sweep, volume helical sweep. Please free to drop any questions at this point. I have a backup model. Maybe I can just look into that. No.
Sir, I think there is no questions from the participant.
Okay.
Uh, we can wind it up then.
Okay. Thanks for the given opportunity. Maybe the session gave some insights of the kind of tools that are available in the field, and I hope it leads to better collaboration between disciplines as well. So these are not exclusively restricted to a mechanical engineer. I see in my field even the electrical engineers, electronic engineers, and also the industrial designers, craftsmen are heavily relying on the 3D development softwares. And it is, so and these days there is no, let's say, it's all on job itself and the kind of hands-on you get. And the more important, the tool should only act as a measuring or as a backup for you to get your ideas into reality. Yeah? So I think with that I can I will take leave for this.
Thank you so much, Chaitanya, for your time and valuable input on this particular topic. I hope this would definitely help all the researchers and academicians, all the practitioners to carry ahead their own research or individual work. And I hope they would be, I hope you won't mind if they come back to you with certain doubts in future as well. So
Yeah, definitely.
Yeah, with that, we thank you. We extend our sincere thanks to you from Gitam team to University Bangalore campus and the whole organizing team and participants as well. Thank you so much.
Okay. Wish you all the best. Bye.
Participants, the session will commence at 2:30. Before logging out, please fill the feedback form. Dear participants, there is a Google link given to you. Please join the class. For the tomorrow session, the practical session, the codes will be shared.